All right, so welcome to Math 140 Calc 2. This is lecture 8. And so what we're going to be doing today is we're going to be doing integration by parts. And so what I want to do is cover a little bit of the theory, talk about how do we apply integration by parts to some interesting problems, and then as time permits, talk a little bit about the theory and applications. All right, so I forgot that since I am using the external screen, I have to actually log on to the computer in here to project so that you can see things. Okay, so I've mentioned this several times. When you have rules for integration, where do the rules for integration come from? Yes. They come from rules for differentiation. So every differentiation rule is responsible for an integration rule. So the question is always going to be, can you recognize what's going on? And sometimes it's going to be very easy to see what's going on. Other times it's going to be very difficult. And so what I want to do today is talk about one of the differentiation rules, which is not as nice as we wish it was. So which is a really nice differentiation rule? The sum rule, right? The sum rule is absolutely wonderful. The derivative of a sum is the sum of the derivatives. The constant rule, a constant times a function is the constant times its derivative. That's a great rule. What's not so great, product, quotient. Chain is not hard, but you have to remember, with the chain, that we have that extra, g prime of x at the end, and that's one of the most forgotten things in calculus. Okay, so today we're going to be concentrating on the product rule and what does that give us when we do integration by parts. And so we're going to do some examples, and one of the big applications is we're going to try to find the antiderivative of the natural log of x. And in college, we try to write log x to mean base e. In high school, we use ln for natural log. Just when you're looking at books, you have to always bear in mind what is the notation people are using. Later today, I will be giving a lecture in multivariable calculus on coordinate systems, and it is perhaps my least favorite lecture to give because I learned the coordinate systems first in physics class, where they switch the two spherical angles theta and phi. And so the physicists do it different than the mathematicians. And given that my paycheck comes through the math department, math stats, I have to remember that I have to use the math notation. But the warning is to just be very careful of where you are coming from. Okay, and then as remarked, I am going to take advantage of the college policy and remove the mask and actually be able to breathe and talk. All right, so can someone tell me what the product rule is for derivatives? So what's the product rule for derivatives? Yes, normally we will write it in this order. The order does not matter. We can write it as either f prime g plus f g prime or f g prime plus f prime g. Normally we do the f prime first. So we can rewrite this, and we've talked about this before, as f prime of x, g of x equals f of x, g of x prime minus f of x, g prime of x. And what's nice about this is that we have three expressions. One of the expressions, when we're trying to find an antiderivative, is going to be extremely easy. So which one do you think is going to be the easiest one to find an antiderivative of? Why the first one? Which one of the three, if I ask you, what's the antiderivative of? Which one is very easy to find the antiderivative of? The second one, right? The second one is I have the derivative of f of x g of x. What function has derivative f of x g of x? Oh, it's the function f of x g of x. So this is easy to integrate. And so if we integrate both sides, we get f prime of x g of x dx equals the integral f of x g of x prime dx minus the integral f of x g prime of x dx. And if you want, rather than integrating from an indefinite integral, we could make it a definite integral. And if we wanted to, we could integrate from maybe a to b. And the second one is going to be really easy. It's just f of x g of x evaluated at a and b minus the integral from a to b of f of x g prime of x dx. And this is the integral from a to b f prime of x g of x dx. And normally the way we write this to try to remember what's going on is we write this as the integral from a to b of u dv equals u at ab minus the integral from ab of v du. So u of x is f of x, v of x is g of x, and dv is g prime of x dx. So let's think about what is going on. So one of the nice things about doing it on the large screen like this is if I want to just take a screenshot, I can do this, I can post to the next one. And then if I'm missing just a little bit, I can hopefully just draw it without too much trouble. What is nice about this? So I overshot the margin a little bit. Okay. So what is nice about this expression? What we really have is we have the integral of derivative of f times g equals boundary minus the integral of f derivative of g. What we're really doing is we're moving the derivative, from f to g in the integral. What's the cost of moving the integral from f to g? Well, the cost is a boundary term, a boundary piece, and a minus sign. You always want to take stock and ask, is this a good trade? So for some problems, I would much rather have the second integral, the integral of f g prime, than the integral of f prime g. Sometimes the second integral is just going to be an easier integral to do. What does it cost me to make that trade? Am I sacrificing my firstborn son? That's a very high cost. I'm not quite willing to do this. Well, all I have to do is I have to evaluate f of x g of x at b and subtract f of x g of x at a. Not a big deal. And I have to have a minus sign in front of the next integral. Again, not a big deal. So this is a very low cost thing to try. If you're going to do integration by parts, what do you have to identify? To integrate by parts, what do we need to identify? So what do you need if you're going to integrate by parts? So it's the formula is integral from a to b of u dv is uv minus ab minus integral from a to b of v du. What do we need to identify? Yes. So we need u and dv, and then from this, we easily get du and v. And so, for example, if, say, v of x is e to the 3x squared, then dv dx, what's the derivative of e to the 3x squared? So that would be e to the 3x squared times the derivative of 3x squared, which is just 6x. So then we would get dv equals e to the 3x squared times 6x dx. So if you're comfortable just going straight to dv is e to the 3x squared times 6x dx, you can just do that. If you want to just first go dv dx is equal to this, and now I'm going to just move the dx over to the other side, you can do it that way as well. So once we have u and dv, we can find du, which is very easy to do because du is just differentiating. Now, finding v from dv could be difficult because that requires us to do an antiderivative. And so there's always work somewhere. So this is where we have the main work. Need to be able to find v from basically v prime of x. And that's not always going to be easy. All right, so let's do an example. So there's a bunch of examples we can do. Here's an interesting one. The integral from 0 to infinity of x e to the negative x dx. This is actually a very important integral. So note integral from 0 to infinity of e to the negative x dx. So what function has derivative e to the negative x? Almost e to the negative x. Negative e to the negative x. So the function that has derivative e to the negative x is negative e to the negative x, because when you take the derivative, you have to take the derivative of negative x, that gives you an extra minus sign. We evaluate this at 0 and infinity. Okay, well, when you put in infinity, e to the negative infinity is, so e to the negative infinity, e to the negative million, e to the negative billion, e to the negative trillion. That's 1 over e to the million, 1 over e to the billion, 1 over e to the trillion. It's basically 0, right? So e to the negative infinity is 0. What's e to the 0? 1. So this is going to be 0 minus negative 1, which is 1. E to the negative x is greater than or equal to 0 for x greater than or equal to 0. This is a probability distribution. Anybody want to guess what the name of this probability distribution is? It's related to the letter you see here. What function is this? So what's the name of the function e to the negative x? The exponential function. This is the exponential distribution. And this is base e. And so if you plotted it, it would look something like this going off to infinity. So if you look at radioactive decay, for instance, that is something that would decay something like this in terms of often how long you have to wait for something to happen. So a lot of processes are given by an exponential random variable. Calculating x e to the negative x, that's just calculating the mean of this random variable. Okay, so let's find the integral from 0 to infinity of x e to the negative x dx. What method of integration do you think we should use for this? What would you guess would be a good integration technique? Integration by parts. So there's two excellent reasons to guess that. One, this is electron integration by parts. And two, that is the only technique of integration we've really covered this semester. So at this point, we really have no choice but to do integration by parts. So we have to tell what do we think u is and what do we think dv is. How many options do we legitimately have in this problem for u? What are the possibilities for u? Yes. Wait, it's either x, it's almost surely either x or e to the negative x. And if you try one and it's not working, what do? Switch, right? If you want to go like that, we'll see if Professor Mawson complains about that. Just complain, throw a temper tantrum. Sure, you can do that. But try the other one. What if the other one doesn't work? Then you go back to the first one and say, maybe the first one wasn't so bad after all, or maybe this is not something that can be done by integration by parts. So now we have to figure out which do we want to try to be u, x or e to the negative x. Again, if it works, we've got a 50-50 chance. If we choose the wrong one, we just go to the other. But if you can save yourself doing extra work, it's worth saving yourself. Any thoughts as to which would we want to try? Got a 50-50 chance. Okay, which do you want to be e to the negative x, u or dv? I'm sorry? Okay, so let's take u to be e to the negative x, then dv would be x dx, right? So I need a function whose derivative is x. So what function would that be? What would v equal? So this is the same as dv dx equals x. So what function has derivative x? 1/2 x squared. So 1/2 x squared. And if u is equal to e to the negative x, what's du going to be? So if my function is e to the negative x, what's its derivative? We just did that the last slide. Good, negative e to the negative x dx. So when we look at this, the integral from 0 to infinity of x e to the negative x dx would be equal to uv, which is 1/2 x squared e to the negative x with a minus sign at 0 infinity, minus v du. The minus signs reinforce, and it becomes plus an integral from 0 to infinity. I can pull the 1/2 out, x squared e to the negative x dx. So do you think this was a good choice at the end of the day or a bad choice? What do you think? We started off with an integral of x e to the negative x, and now we have an integral of x squared e to the negative x. Thoughts? Yeah, this made it worse. This is how you learn. We started off with we knew earlier how to integrate e to the negative x. The problem was we had x e to the negative x, so that was making things harder. So rather than integrating x e to the negative x, we're going to use integration by parts to change the integral. And unfortunately, by choosing it this way, we made the integral harder. We now have to integrate x squared e to the negative x. Fortunately, there are only two choices today for this problem. Are there any Seinfeld fans here? Have you seen the episode The Opposite, where George Costanza realizes that every decision he's made in life is wrong? And so his friends convince him that from this point onward, he should do the opposite of his instincts. What's wrong with this idea in general? If every instinct you have is wrong, why not just do the opposite? So from Zoomland, there could be more than two choices. If there's only two choices, when you're transmitting information, this is extremely important. We transmit zeros and ones. If you know you mistransmitted, great, I can correct that. And this is how a lot of modern communication, e-commerce, crucially depends on base 2. And if you know there's a mistake, you can easily fix. In life, it would be wonderful if there's only two choices so that if you know something is wrong, you know how to fix. That's not true in general. But as a special today, since we're just starting off, there's only two real choices for this problem. So now, what should we try for u? Let's try u equals x. So dv is e to the negative x dx, or dv dx is equal to e to the negative x. Okay. What function has derivative e to the negative x? So what function has derivative e to the negative x? Yeah, negative e to the negative x. That's not so bad. And if u equals x, what's du going to be? It's going to be 1 dx. Or we can just write dx. But basically, we get du dx equals 1. So our integral from 0 to infinity of x e to the negative x dx is going to be equal to uv at 0 infinity minus the integral from 0 to infinity of v du, and just putting everything in. So I'm just writing that extra line to just go really slow, to have everything in front of us. The more of these problems you do, the faster you go. So I have been doing these problems far longer than you've been alive. At this point, I don't need to write this down anymore because I've done it way more times than I think anybody ever wants to integrate problems like this. But when you're starting out, it's very easy to miss-substitute. So if you take the extra moment and just write down, here is the formula I'm substituting in. Notice I have everything I need up above. I have what u is, I have what v is, so I can substitute in very easily. So I'm going to get uv, that's negative x e to the negative x at 0 infinity, minus v du, the minus signs reinforce, I have plus an integral from 0 to infinity of e to the negative x dx. Okay, now what about x e to the negative x? When I put in 0, what is x e to the negative x at 0? 0. I've got 0 times 1, which is just 0. What about when I put in infinity? Then I'm going to have infinity times e to the negative infinity. It is going to be 0. So we'll justify that in a moment. So this is just 0. Does anybody know what the integral of e to the negative x is from 0 to infinity? Well, let's think, could it be 0? What kind of function, what can you tell me about the values of e to the negative x? What kind of numbers are e to the negative x? Well, when we say fractions, we normally think of rational numbers. So think of it positive, negative, 0, complex, real. What can you say about the values e to the negative x? Yeah, well, let's do this and then we'll talk about. What can you tell me about the values of e to the negative x? What kind of numbers are they? Okay, but what kind of fractions? Positive, negative, complex. What kind of numbers is e to the negative x? Could e to the negative x, is it a real number? Let's start with that. Yes. Could it be negative? We have e to the negative x. So there's a comment from Zoomland that it's positive. But e to the negative x is always going to be a positive number. It's 1 over e to the something. The exponential function is never negative. X can be positive or negative, that's fine. If x is negative, then you're going to actually have a large number. So we know we're integrating something that's non-negative. So we expect that this number can't be 0. So without even doing the integration, I know this integral is positive. I claim we actually know what the integral of e to the negative x dx is. Can somebody define foreshadowing? Yeah, so I mean, there's a great line by Chekhov. If you're describing a room and there's a gun in scene 1, that gun should be fired by scene 3 or something like that. One of my students had asked me to read some of Chekhov. So whenever people ask me to read something, I try to do so. There's actually a Final Jeopardy question recently, and I kicked myself for missing it. Foreshadowing, you put stuff there to indicate that it's going to be coming into play later. What did we do before we actually evaluated this integral? We evaluated the integral just of e to the negative x dx, the simpler integral, and we saw that that equals 1. So we know that this over here is just 1. So the answer is 1. We still have to justify this, and we'll justify that in a second. You had a question?
Yeah, my question was just why was e to the x to the negative x not be negative e to the negative, but then I just realized that you switched.
Yes, I switched the sign outside. So the only thing we have to look is I owed you the following. Just check the chat. And so I owed you that the limit as x goes to infinity of x e to the negative x is 0. This is the limit as x goes to infinity of x over e to the x. What can we use to evaluate this? Anybody remember what do we use to evaluate this? What does the numerator go to? As x goes to infinity, what does the numerator go to? Infinity. What does the denominator go to? Infinity. So looks like infinity over infinity, use what? What do we use? You know you've made it when your name is a verb. So from Zoomland, we have L'Hopital. So we use L'Hopital's rule. And what L'Hopital's rule says is if you have infinity over infinity or 0 over 0, the limit of f over g is the same as the limit of f prime over g prime. So this is the same as the limit as x goes to infinity. What's the derivative of x? It's just 1. And what's the derivative of e to the x? E to the x. And so what is this limit going to be? 1 over e to the x as x goes to infinity. That's just going to be 0. And that finishes our proof. So sure. So L'Hopital is the following. If the limit as x goes to a of f of x over g of x is 0 over 0 or infinity over infinity, then it is equal to the limit as x goes to a of f prime of x over g prime of x. And the proof is actually pretty nice. If we look at the limit as x goes to a of f of x over g of x. Okay, what I'm going to do now is I'm going to just put in some extra stuff. Let's do f of a equals g of a equals 0. Let's do the case when f of a and g of a equals 0. If f of a equals 0, can I just subtract off f of a from upstairs? Yeah, why? Why can I subtract off f of a? Because it's 0. I can subtract off g of a downstairs. I can divide by x minus a over x minus a because I'm multiplying by 1. If I divide the numerator and denominator by the same thing. So what this really looks like is this looks like the limit as h goes to 0 of f of a plus h minus f of a over h divided by g of a plus h minus g of a over h, which is just f prime of a over g prime of a. And that's why L'Hopital is true. This is a rough justification of where L'Hopital's rule comes from. This is the case of 0 over 0. Infinity over infinity is a little bit more work, but if I have 0 over 0, I can just subtract f of a and g of a. I haven't changed anything. I divide the numerator and denominator by the same thing, and I haven't changed anything. And I just take the limit. What if f prime of a over g prime of a is 0 over 0? Do I kick the wall again in frustration? That would probably bring Professor Morrison over. So let's try to avoid kicking the wall in frustration. What would you do if you had 0 over 0? Do it again. And what would you do if you had 0 over 0 again? And so hopefully, eventually, you stop having to L'Hopital, that eventually you no longer have 0 over 0, and then you have your answer. And so if I give you, for example, let's say I give you cosine x minus 1 over x squared as x goes to 0. What does the numerator look like? What does cosine x minus 1 look like as x goes to 0? What's the cosine of 0? 1. So numerator looks like 0, denominator looks like 0. Note this is 0 over 0, can use L'Hopital. So we would have the limit as x goes to 0 of cosine of x minus 1 over x squared is the limit as x goes to 0. What's the derivative of cosine x minus 1? So what would be the derivative of cosine x minus 1? Excellent, negative sine x. And the derivative of x squared is 2x. And what do we have now as x goes to 0? What does the numerator look like? So what's the sign of 0? 0. So it's still 0 over 0. So use L'Hopital again. So this would be the limit as x goes to 0. What's the derivative of sine of x? Negative cosine. So we get negative cosine of x, and then we would have 2 down below. Oh, this is clearly no longer going to be 0 over 0 because the denominator is not 0. Excellent. What's the cosine of 0? 1. So this limit is just going to be negative 1/2. Okay. So now you're going back to integration by parts. I could give you the integral from 0 to infinity of x squared e to the negative x dx. Now we have more possibilities for u. What could u equal? So what are some possibilities for u? Someone tell me options for u. There's other possibilities. I'm sorry? Well, negative x and x is really the same thing. It's up to your minus 1. But you could just do x, which is the same as your negative x. So it could be x squared. It could be e to the negative x. It could be x. What else could it be? There is one other possibility. So what would that be? You could do that, and then you wouldn't have anything. So you could do x squared e to the negative x. You could do x e to the negative x. And you could do 1. So there's a lot of possibilities. Which one do you think is going to be the one to try? Yeah, this is the one that you want to try. And when you do this, what should happen is you should get an integral involving x e to the negative x, which we know how to do from before. And if I gave you x cubed, that would give you an integral involving x squared. So you could try these games. And so as an exercise, do the integral from 0 to infinity of x squared e to the negative x dx, integral from 0 to infinity x cubed e to the negative x dx, integral 0 to infinity x to the 4th e to the negative x dx. Make a conjecture for the integral from 0 to infinity of x to the n e to the negative x dx, and prove it. It turns out these integrals are extremely important, and they are related to a sequence of numbers you should have hopefully seen in probability. But the whole point is trying to figure out what you want to do. All right, what I want to do now is I want to do an interesting example. Let's integrate from, let's do from 1 to n of the natural log of x dx. Do people prefer me to use ln rather than log? I will try to use ln at the beginning of the semester. If I ever slip and use log, though, we're always using things base e. I will try to do ln. So I want to integrate ln of x. So what do we know about ln of x? Do we know its derivative? Okay, what's the derivative of the natural log of x? Do we know its antiderivative? Do we know what function has derivative natural log of x? No, that's what we're trying to prove here. What technique do you think might be useful to find this antiderivative? What method of integration should we use? Integration by parts. One, as I said earlier today, it's a lecture on integration by parts. It could be evil. I have done that before. Never in a calculus class, only in advanced upper level classes. My favorite exam question was, there was a problem, there was two parts. Part A for 5 points, is the following object a ring? And then for 15 points, part B, is it a very special type of ring? Is it an integral? And so I was at Brown, and 2/3 of the students wrote, it has to be a ring, else why would you ask part B for 15 points? It wasn't a ring. It failed the property that everybody always forgets to check. I'm not going to do something like that. This is a lecture on integration by parts. This is the only technique of integration we know so far. We should be doing this as an integration by parts problem. All right, well, if we're going to do that, we have to figure out what is u and what is dv. Now, for integration by parts, we're thinking we need two functions. Do you see two functions here? So there has to be another function hidden. What is that hidden function? One. Really what we have is, we have the integral from 1 to n of 1 times the natural log of x dx. So we have to decide, where do we want to put u, where do we want to put dv? Well, given that we do not know what function has derivative natural log of x, where should we put natural log of x? It's got to be the u. And so what does dv have to be? It has to be 1 dx. So what would v equal? It would just equal x. And what would du equal? 1 over x dx. And so again, I want you to see that this is a natural thing to try. But it's interesting. There are two functions here, but one is hidden. And you can interpret but one is hidden two different ways. Depending on how you pass it, it's still true. One of the functions is hidden, or the function which is 1 is the one that is hidden. How many people know the sentences eats, shoots, and leaves? You ever heard of eats, shoots, and leaves? I think it's koala bears. Depending on how you pass, they can either eat, shoots, and leaves, or the koala bear eats, shoots something, and then leaves. There's a lot of sentences where, depending on how you punctuate, you can get very different interpretations. There have been some multi-million-dollar lawsuits that have been decided by the Oxford comma as to whether or not you have to put a comma when you're listing 3 elements, in terms of, does this preceding part apply to the later stuff? Really think long and hard about how you are writing things. So for what we're doing here, we have the integral from 1 to n of the natural log of x dx equals u of x v of x at 1 and n minus the integral from 1 to n of v du. So u of x v of x is going to be x natural log of x at 1 and n minus the integral from 1 to n of v du. Oh, what is v du? So what is v du? It's 1 dx, right? It's just 1 over x times x dx, which is just x natural log of x at 1 and n minus the integral from 1 to n of just 1 dx. Life is good. right? This is integration by parts at its finest. We take a really difficult integral, the integral of the natural log of x, and by switching where the derivative hits, it's now hitting, and now we get the integral of 1. And so the whole point is we viewed natural log of x as 1 times natural log of x. This is one of the hardest things to learn how to do in mathematics, to do nothing. There are 2 ways to do nothing. Can someone tell me how you can do nothing? I'm sorry, add 0, and what else? Multiply by 1. And when you look at our proof of L'Hopital, we actually did both. We added 0 and we multiplied by 1. That shows you how great of a result L'Hopital's rule is. Okay, now we just substitute in. So this is going to give us n natural log of n. And you can see now why a lot of people don't like writing natural log, because n natural log of n, oh my God, this is a message, right? Especially with my handwriting. Minus the integral of 1 from 1 to n. What's the integral of 1 from 1 to n? Yes. So what's the integral from 1 to n of 1? So this is just going to be what function has derivative 1? It's x. We evaluate that from 1 to n, and that's going to just be n minus 1. We basically have a constant function of height 1. The width is just from 1 to n, that's just the length n minus 1. So it's just going to be n minus 1. So it's just minus n minus 1. So we get the next page, we write it. The integral from 1 to n of the natural log of x dx is equal to n natural log of n minus n plus 1. And it turns out this is one of the most important integrals to do. So can somebody tell me what is 3 factorial? 6. How'd you get that? 3 times 2 times 1. N factorial is n minus 1, 3 times 2 times 1, and we set 0 factorial to equal 1. So if I give you n factorial, and I want to understand how big n factorial is, it's going to be a huge number. Do we know any functions that take large numbers and make them reasonably sized? Log. Do we know any functions that convert products to sums? Log, right? It fits both bills, right? So you should have a Pavlovian response. Who was Pavlov? Researcher with the dogs, and he basically trained the dogs so that when they heard the bell, they would start salivating and they would expect meals would come. There are stories, I went to Yale, that MIT students trained pigeons so that when they heard whistles before the football season began, they would fly and eat bird seed that was placed there. So when the football season began and the officials started to blow the whistles, birds just came from everywhere. So you should have a Pavlovian response. Whenever you see a product, think logarithm. It might make the relationship a lot easier. Well, the log of n factorial is the log of n minus 1, ... 3 times 2 times 1. Or if I write it the other way, 1 times 2 times 3 times n minus 1 times n is the log of 1. Sorry. I'm trying to use natural log. Trying to use the one. Natural log of 1 plus the natural log of 2 plus the natural log of n. This is approximately the integral from 1 to n of the natural log of x dx. And this leads to what you'll cover in Calc 3, the integral test. And you can use this to get more refined estimates. I am just trying to give a really quick, high-level application without going into all the details. But I'm essentially replacing my function, saying it's constant on intervals of length 1. So first its value is the natural log of 1 from 1 to 2. Then it's the natural log of 2 from 2 to 3. Then it's the natural log of 3 from 3 to 4. So this should be pretty close to the true answer because the logarithm is changing very slowly. So what this tells us is the natural log of n factorial is approximately n natural log of n minus n plus 1. Well, if I know the natural log of n factorial is this, what does that tell me about about n factorial? What would n factorial be approximately? So if the natural log of n factorial is approximately n log n minus n plus 1, what is n factorial approximately? So if I tell you your natural log is 3, what number has a natural log that's approximately 3? So what function would have natural log approximately 3? So if the natural log of x is approximately 3, then x is approximately what? What function? Why 9? E to the third. Right. The natural log of e cubed is just 3. If I tell you the natural log of x is approximately 10, then x is approximately what? E to the 10th. So if I tell you the natural log of n factorial is about n log n minus n plus 1, what should n factorial be approximately? So how would you continue the pattern? So I got from Zoom e to the negative n factor, not quite. So we have the natural log of n factorial is this whole expression over here. E to the n log n. Anything else? Minus n plus 1. And the reason I'm doing this is this allows me to practice laws of exponents. This is e to the n natural log of n, e to the negative n times e. And this is just a way for me to review exponent rules. If it's been a long time since you've done algebra, exponent laws is one of the many things that is put into deep storage. And so it's not bad to just quickly review. If I have the exponential of a sum, it's the product of the exponentials. The log rules come from the exponent rules. All right. The only one that's hard is e to the product. All right. Well, if I want to deal with e to the product, then this is the same as e to the natural log of n to the nth power, e to the minus n times e. And I'm just using my product laws. What is e raised to the natural log of n? So there's a nice answer for e to the natural log of n. What is e to the natural log of n? It's just n. The natural log of n is how many powers of e I need to get n. I raise e by the number of powers of e I need to get n. And so I get n factorial is approximately n to the n, e to the minus n times e. And the actual answer is n factorial is approximately n to the n, e to the minus n square root of 2 pi n. And just doing this really simple calculation gives us a nice rough sense of what's going on. So this is a good place to stop for today. So we actually did a tremendous amount. We did integration by parts. We saw integration by parts came from one of our differentiation rules. It came from the product rule. We saw how to do integration by parts, and we have to identify what is U and what is dV. The more choices you have, the harder it's going to be, and you just start doing something and you hope it works, and if it doesn't, you backtrack. And then you try to say, well, which is a good choice to make? And then we ended by looking at the natural log. I'm sorry, we used L'Hopital's rule to get one of the problems, which was nice. We looked at the natural log of x, and we noticed we had to write that as 1. And this integral turns out to really matter. It allows us to estimate a factorial. Later in Calc 3, you'll learn how to do this a little bit better. All right, so this is a good place to stop. Have a good rest of the day. Enjoy the glorious weather.